Hello there. Today I want to talk about big O notations, linear search, and binary search. So let's start with linear search. Linear search. Alright, let's also have a list in place. And this list have 6 numbers 1 2 3 4 5 6, and those numbers are 1 3 5 7 8 9. All right, and we want to find 9 inside this list. We can also call 9 as the key. Okay, so what we would do in a linear search is just compare 9 with every single element in the list and say, is 9 equal to 1? No. Is it equal to 3? No. 5? No. 7? No. 8? No. And 9? Yes. So that's how linear search works, and it's alright. We do get to say whether the element is there inside the list or it's not there, but we can do better because if we are going to do this, if we are going to do linear search, it's not really efficient. What happens when we have a million numbers? What happens when we have dot 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 dot? So this is the first element and this is the 1 millionth element. What happens when we want to search something and that's at the very end of the list? We basically go through every element, and that's a huge waste of time. So we can do better, and that's where binary search comes in. But before we talk about binary search, let's talk about big O notations. So big O notation. So what is it? It's math. Yes, it is. But it's not the boring kind of math, so you don't have to worry about going into specific details here. So what it is basically a way for us to measure the performance of a given program relative to its input. In this case, if for linear search, the big O notation would be big O of n, because it's taking us n comparisons in the worst case. N comparisons, that's the most important part. In worst case. Alright, and n is the length of the list, which is 6. And I think we can do better with binary search, so let's see how that goes. Binary search, let's copy this whole thing right there, and then for binary search, what we are doing is we're basically breaking the list into half. So the length of the list is 6, half of it is 3. This is going to be our middle element. Compare this with 9. Nope, it's not equal to 9. So we are going to look at dividing the list into half. Let's see, 9 is greater than 5, right? Yes, it is. So we are going to look at right half of this list. And why this works? Because the list is sorted. If it was not, then this comparison would make no sense. But since the list is sorted, binary search works. And 9 is greater than 5, so we are just going to look at this part, and let's copy this down here. 7 8 9. Now for this one, the middle element is this. Comparing it with 9, nope, it's not equal to 9, so we do the same thing over again. 9 is greater than 8, so just look at the right side of this list, and since we just have one element, we will call that the middle element and compare it with 9. Yes, it is equal to 9, so let's return true. We found the element in the given list. And if you notice, this is only taking us 3 comparisons, 1, 2 and 3. That's interesting, right? We have just broken down the 6 comparisons part. Let me just highlight that. 6 comparisons into just 3 comparisons, and that means we are dividing the performance in half. And whenever that happens, we will basically say that the program is performing with big O of log of n. Alright, so let me just quickly highlight this. This is for linear search and this is for binary search. Alright, that's all in this video. I hope you like it, and if you want me to do more of these, let me know in the comments. I'm going to talk more about algorithms, data structures and computer science going forward. So do subscribe if you're interested in those topics, and thanks for watching.